In this video, if you look at the Zener diode characteristics, you will see current is increasing, but voltage across Zener is constant at Zener breakdown voltage. For this property of Zener diode, it is used as voltage regulator. Now, what is Zener diode and what is Zener breakdown? In this video, I shall explain the mechanism of Zener breakdown with necessary animations. I have mentioned some numerical figures like 100 angstrom to 1000 angstrom or 2 to the power 7 volts per meter or 2 to the power 2 into 10 to the power 6 volts per meter or 2 into 10 to the power 7 volts per meter or something like that. If you like to avoid such figures, there is no problem. Only note that whether it is very small like 100 angstrom or 1000 angstrom or whether it is very large quantity like 2 into 10 to the power 7 volts per meter or 2 into 10 to the power 6 volts per meter. The exact figure is not so important, but the magnitude, but the amount, whether it is small or large, it matters. So, don't bother about the figures. Only note that whether it is very small or very large. That will be sufficient to understand the physics behind Zener breakdown. Moreover, in this video, series limiting resistance, variable power supply, milliammeter, voltmeter, load resistance, etc. all are omitted intentionally to give stress on theoretical explanation of the Zener breakdown mechanism. For practical purpose, the circuit scenario will be different. The violet color where fixed with the Zener is actually of silver colored in reality. Magnified view of the atoms, electrons, semiconductors are depicted for better explanation in this video. Silicon has barrier potential of 0.7 electron volt. Electron and holes, here 5 electrons and 5 holes. Here also, this is the Zener diode and this is the ordinary diode. 5 electrons in N side and 5 holes in P side, for example. Actually, there are so many electrons and holes are there. Majority carriers are holes in P side and majority carriers electrons in the N side. But for the comparison of Zener diode and ordinary diode, I have considered only 5 electrons in Zener diode as well as 5 electrons in the ordinary diode in the N side. Similarly, 5 holes in the P side in Zener diode and 5 holes in the ordinary diode. But look at that, the number of electrons, that is doping concentration being very high in the Zener diode, the width in which it is available is very small here. Same number is available in the larger width due to lower doping concentration. This is the difference between these two pictures. I am repeating again. Since the cross section of the two diodes are equal, for comparison of the two diodes, we have taken two diodes of the same cross-sectional area. So here, due to the large doping concentration in Zener, these 5 electrons are available in the smaller width, whereas same number of electrons are available in the larger width. As they are straight, the doping concentration is small. With this picture in mind, look at this animation. electrons and holes, here 5 electrons and 5 holes, creates this barrier potential as a result of recombination. In the smaller width of depletion region, this is the depletion region between blue and green, and here between two white lines. Smaller width of the depletion region in comparison to ordinary diode. Here you remember that each electron and hole leaves behind positive donor atoms and negative acceptor atoms respectively. These atoms, these ions, create barrier potential. Here, for example, 5 electrons and 5 holes recombining at the junction create this necessary barrier potential 0.7 electron volt. Here is also 0.7 electron volt, but for silicon. Then in ordinary diode, it will require 5 electron and 5 holes to recombine at the junction to create same barrier potential of 0.7 electron volt at the junction. But look, these 5 electron and 5 holes are available at a larger volume in ordinary diode in comparison to Zener diode due to lower doping concentration in ordinary diode. Thus a greater volume, that is width, as cross section of the diodes are same in ordinary and Zener diode, is required in ordinary diode to provide same number of electron and holes to create barrier potential of 0.7 electron volt. Thus, in a nutshell, the barrier width is smaller than the barrier width of ordinary diode with unbiased Zener diode or ordinary PN junction diode. This is unbiased. These two diodes are unbiased diodes. Previous one was the unbiased PN junction. Here it is biased PN junction. With the same battery voltage, this is the positive of the battery, this is the negative of the battery. Negative is connected to the P side, this is the Zener diode. This is also ordinary diode connected to the P side. This is connected with the same battery. This is the N side connected with the positive terminal of the battery, and this is the N side is connected to the positive terminal of the battery with the same battery voltage. So for the comparison purpose, reverse bias, as positive is connected to the N, negative is connected to the P, positive is connected to the N of Zener diode as well as negative is connected to the P of the Zener diode. So both diodes are reverse biased with the same battery voltage. So for the comparison, it is VD, say. So note that two potentials applied to the two diodes, one Zener diode, other is ordinary diode, is same reverse bias is applied to the both the diodes. With the same reasoning, when a reverse bias, negative of battery at the P end and positive of battery at the N end of the diode is applied, the width of the depletion region of the Zener diode will increase. Look at the animation. It increases. It also increases. And compare the two cases. As soon as the switch is turned on, the width of the depletion region increases, but in Zener diode, thickening is not so much. Thickening is there, but not so much in comparison to the thickening is there, but not so much as in ordinary diode. Ordinary diode thickening is more than the thickening of Zener diode. Look at the initial position. This was the initial position. This is the width of the depletion layer between blue and green lines. Here also blue line and green line. So depletion layer unbiased, in unbiased condition, is also as explained just in previous slide, that the depletion layer, width of the depletion layer in Zener diode is smaller than the width of the depletion layer in the ordinary diode. This unbiased condition, switch is open. Look at the animation, look at this position of the switch. As soon as switch is closed, it increases, and the width of the depletion layer is still now much less than the width of the depletion layer in the ordinary diode. It thickens, but not so much as in ordinary diode. So reverse voltage applied at the diodes are same in both the cases. Say VD, V suffix D. Concentration level in the Zener diode being high, so to produce same reverse potential VD across the depletion region, a smaller thickness is sufficient to provide same number of electron and hole pair. Now we know electric field is negative of dVdx, but here voltage is negative, reverse bias, and voltage is uniform. This uniform potential creates a electric field that's equal to V upon D. V is the applied voltage, here it is say Vd, and D is the thickness of the depletion layer. So in case of Zener diode, this thickness is dz, and in case of ordinary diode, this is d ordinary. Since dz is much small than the d ordinary and V applied voltage is same in both the cases, then in case of Zener diode, the denominator is less, so this value is higher. So Ez is much greater than E ordinary. Here the glowing object is the Zener diode. Red end is P side and black end is N side. The symbol of the Zener diode is this. The red triangle is the P, and this straight line with some chords here and here is N side. This is the symbol of Zener diode. The pink strings or wires are connecting wires. These pink wires are fixed with the Zener diode and they are used for connecting the necessary wires with it. Blue wire is connected with the negative terminal of the battery, and the red wire is connected with the switch, and switch is connected to be connected with the positive terminal of the battery, so it is reverse biased. Negative terminal is connected to the P, so it is reverse biased. Zener diode is reverse biased. As soon as the key is closed, look at this key. It's very important. Look at this position of the key. It is now open. Look this animation. As soon as it is closed, current will increase. Current will start, as because this voltage is above the Zener breakdown voltage, so high current will flow, which is shown graphically. This is the voltage, negative voltage along negative x-axis, and this is negative current along negative y-axis. This is the initial position 0 0 origin of the graph, and this is the origin. At the origin there is a green dot which indicates when the voltage is 0, current is 0. Here it is open, so current is 0. Here current is 0. Here voltage is 0, so current is 0, which is indicated by the green dot at the origin. Now note that if the potential is less than Zener breakdown voltage, then also there will be a current which is called minority current due to minority carriers. But here the voltage of the battery is higher than the breakdown voltage. So look at the animation, look at the position of the key. In the graph, V is negative voltage axis and I is the negative current axis. Reverse voltage and reverse current is plotted here. When voltage is 0, K is open, I is equal to 0, denoted by the green dot. As soon as voltage is increased, current will increase as shown in the figure. In a PN junction diode, in the inside there are pentavalent positive donor atoms like arsenic. In P side there are trivalent negative acceptor atoms like aluminium. Electrons are majority carriers in inside and minority in P side, whereas holes are majority in P side and minority in N side. So, electrons diffuse from inside to P side and holes from P side to N side. Look at this animation. At the junction, electrons and holes recombine, leaving behind positive donor arsenic atom and negative acceptor aluminium atom, respectively. At the junction, a barrier potential is formed due to these immobile charges, which prevents further flow of majority carriers, but helps flow of minority carriers. This region is depleted of mobile charges because arsenic and aluminium are bound to silicon atoms, not shown in the figure, but they are bound with the silicon atoms with covalent bonds. So this region is called depletion region. I have discussed all these in more details in my video on semiconductor diode. I shall further suggest you to go through my video on band theory and semiconductor, which will help you in understanding quantum mechanical tunneling of electron from p side valence band to conduction band at N side. The phenomena of Zener breakdown was theoretically explained by Zener by quantum mechanical tunneling through the barrier at the junction. In tunneling phenomena, an electron confined by a potential barrier of height higher than the energy of the electron is shown to have a finite probability to pass through the barrier, and a finite probability of this electron is there in this region, just like this. Now, it is important to note that minority electrons are flowing as usual. These free electrons are minority electrons. These are minority electrons. These electrons are minority electrons in p side, and these electrons are majority carriers in n side. Holes are minority carriers. Those holes are free. But these electrons are bound electrons. These free electrons, as they are minority, this current is flowing as usual because this barrier helps this flow of electron. This positive arsenic attracts these free electrons, but this current cannot explain the large Zener current. So I am not talking about free minority electron, but talking about electron in the valence band, that is otherwise bound electron to aluminium in p side, which are large in number, as aluminium is large, as the number of aluminium is large. now to tunnel through the junction and goes to N side. As if large electric field at the junction tear the electron out of covalent bond, naturally a hole is in the p side, as if hole is coming from N side to p side. N side to p side, the whole white holes are coming. Electrons are going tunneling through this potential. The field strength starting the process is about 2 into 10 to the power 7 volts per meter. This value can be reached at or below 6-fold for heavily doped. How much? The donor concentration is greater than 10 to the power 19 per cc, corresponding to a doping in excess of 1 part in 10 cube. The probability of tunneling is increased with the decrease of width of the depletion region. It is almost 100 angstrom to 1000 angstrom. This tunnel through this barrier height is so high, normally it cannot penetrate through this, but quantum mechanics says there is a finite probability to find the electron in this region. This is called quantum mechanical tunneling. So Zener explained this phenomena with the help of quantum mechanical tunneling, which can be explained more precisely with the band theory. I am coming to that point, but here it can be explained in another fashion, that as the electric field is very high in this region, as this width is very narrow, as I have already told, so electric field in this region is very high. This high electric field tears the covalent bond and produces so many electron and hole pair, and that electron hole pair creates the large Zener current. But note that these are the valence electrons. So if we want to explain this phenomena quantum mechanically with the help of quantum mechanical tunneling, we have to understand this from the band theory. I am showing this in the next slide. But in that case, it is very important. These are the bound electrons which are tunneling through this potential band. In this diagram, the energy band diagram, we plot the energy of an electron which has a negative charge. Due to charge transfer, p side acquires a negative charge, and for this p bands are slightly raised relative to the n bands. Clearly, in equilibrium condition, the conduction bandage ECP, in the p side will be at higher level than the conduction bandage ECN in the n side. Similarly, the valence band edge VBP, valence band edge EVP in the p side will be at higher level than the valence band edge EVN in the n side. Here we have used the subscripts p and n to indicate the p side and n side of the junction. The condition that the barrier be less than 100 angstrom or 1000 angstrom thick is a necessary but not a sufficient condition for tunneling of electron from p side valence band to n side conduction band. It is also required that occupied energy states exists on the site from which the electron tunnels, and also allowed empty states exist on the other side into which the electron penetrates at the same level. Show the animation. These are at the same level. In the same level. So we have to consider the energy band picture when the impurity concentration is very high, this band structure is quite different from the ordinary junction. So I am repeating this, that the tunneling of electron from p side to n side, p side valence band to n side conduction band, it is also required that the occupied energy level, energy states, exist on the side from which, these are the occupied valence band, from which the electron tunnels. Electron initially was in the occupied valence band, from which the electron tunnels and also allowed empty, here should be empty states exist on the other side, in this side, into which the electron penetrates at the same energy level. Look at this, at the same energy level. That is very important. Only the thickness of 100 angstrom or 1000 angstrom is a requirement, but not a sufficient condition.